everyone, welcome to the course Structure Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today we are at the 21st lecture in the course of Structure Analysis. Last lecture we are discussed about the concept of influence line, and today's lecture we are going to discuss about how to calculate the reaction force by using the concept of ILD. 21st lecture, the title is ILD for reaction force, and at the end of the lecture, student can able to apply the concept of ILD for calculation of the reaction force for a simply supported beam. Okay, we are going to discuss about the ILD for the reaction force. So, ILD represents a graph of functions like a reaction, shear force, bending moment for various location of unit load under the span to calculate the given quantity. So, let me discuss. So, ILD for reaction force, what we are seeing is a simply supported beam subjected to a single point load. So, the single point load is a 1 unit. There was any unit I am using, it's a kilonewton or newton, it's a 1 unit. Okay. And then the length of the span is L. Where exactly this 1 kilonewton load is located, x distance from the support A, and then the remaining distance we say it is the L minus x. So, I am just going to take the moment at summation of all the bending moment at the point B is equal to 0. So, what are the, I am just going to calculate the value of RA. So, taking moment at the point B. So, what is the RA value? RA multiplied by L. Okay. And then here you can see the 1 unit force is acting downward direction. So, minus of 1 into this distance, remaining distance is L minus x. Overall distance is L, and from support A to this 1 unit force, the location is x. What is the remaining distance? The remaining distance is L minus x. Okay. So, this is L minus x, and then the moment at the point B is 0. So, this is what I have written here. Okay, so RA is equal to, I am taking right hand side, this will become L minus x by L. So, we computed the value of RA is nothing but L minus x by L. Now, similarly, I am taking moment at A equal to 0. So, I am computing RB. So, RB multiplied by the linear distance L, and then the minus 1 multiplied by the linear distance x. So, RB is nothing but x by L. Okay, it's very simple. I am taking the moment at B, calculating RA, and then I am taking the moment at A and calculating the value RB. So, we got the RA value is L minus x by L, and then RB value is x by L. Now, let's construct the ILD for the reaction force RA. How to construct? We got the value RA, right? We got the value RB. Now, I am going to put x is equal to 0 in RA value. If you put x is equal to 0, then what it means? X is equal to 0 means, for example, I will draw the free body diagram. If you put x is equal to 0, we consider this load exactly acting at the support. Then what is the reaction force at that time? So, this is the value of L minus x by L is nothing but the value of RA. In this x I am putting 0. So, L divided by L, if you cancel it, it will become 1. Now, I am going to put x is equal to L. X is equal to L means in the beam, now I am substituting, I am applying this 1 unit force at the support B. Okay. So, L minus, then RA is L minus x by L. In this x I am putting L. So, what it will become? L minus L divided by L. So, L minus L is 0, 0 divided by any term 0, it is 0. So, we got the 2 ordinates. At the RA we have the ordinate of 1, and then RB we have the 0, which is forming the triangle. So, this is the ILD for RA. Similarly, we see ILD for the reaction force B. So, already we know this is the RB value. For RB, I am going to put when x is equal to 0. So, we know the RB value is x by L. In that, we are going to put x is equal to 0. You see here, x is equal to 0, we are going to substitute. So, 0 divided by L, 0. And I am going to put x is equal to L. So, L by L will become 1. So, this time I am getting 0 and then 1. So, what we are having here, this is the ILD for RB. Now we are calculated, we have drawn the diagram for ILD for RA and then RB. Now we are going to see how to apply this RA ILD diagram and then ILD for RB to compute the real reaction force. For example, I have taken the example problem here. The problem you can able to say it is a simply supported beam carrying a 3 concentrated loads of 100 kilonewton and then 50 kilonewton and then 200 kilonewtons spaced 3 meter intervals. Okay. So, calculate the reaction at B for the given loading condition. Let's calculate. Once again I have taken the beam and then what I am going to calculate? I am going to calculate the RB value. This is the diagram. I will tell you one simple trick to remember the shape of the diagram. For example, this is our given beam. Consider some load is moving, which is W per meter. This is support A and support B. So, we need to calculate the reaction force RA, RB. Okay. If you want to calculate the value of RA, then at the A point we are going to have the maximum ordinate and then B will be 0. This is for ILD for RA. Now, ILD for RB. At B I am going to have the maximum ordinate 1. So, this is 1. Okay. So, this is for ILD for RB. So, it is very easy to remember. So, here what I am going to calculate? I am going to calculate the ILD for RB. So, this diagram I have taken here. After taking the diagram, simply we need to draw the ordinates where exactly loading is acting. For example, I will draw here. Simply I am extending the load where exactly acting, I am drawing the ordinate. Similarly, you can see this 50 kilonewton where exactly acting and then this 200 kilonewton where exactly acting. Okay. So, I have drawn the ordinate. Now, using the similar triangle principle, I need to calculate the each ordinate height. How to calculate? Let's say this is x1 and this is x2 and then this is x3. So, whatever I have calculated here, one time I will write it here for a more clarification. First, I am going to consider the overall entire triangle. So, what is the overall entire triangle height? The overall entire triangle height is 1. You see the maximum value 1 divided by the span is 10 equal to. Now, first I am going to compute the value of x1. I don't know what is x1. So, x1 divided by. So, for x1 I am going to consider this triangle. See here, I am going to draw in green color this triangle. So, this is a similar triangle principle. Okay. So, what is the length of the green triangle? 2 meters, 2 meters, 3 meters. So, totally it is a 7 meters. So, this is x1 by 7. Okay. So, from this I can able to calculate the x1 value which is 0.7. Similar way I am going to put this 1 by 10, I am going to calculate the value of x2. Okay. So, if it is a x2 then the another triangle is put it in a different color. For example, we will take a pink. Okay. So, this is the x2 triangle. Now, you see the x2 triangle 2 meters, 2 meters, it is a 4 meters, right. So, it is 4 meters. So, I got the value of x2 is 0.4. Similarly, 1 by 10, x3 by, for example, this is the x3. Now, x3 triangle, let us draw in the different color once again. Let us take orange. So, this is the x3 triangle. I have marked in orange color. That base of the triangle is just 2 meters. So, I am getting 0.2. So, I got the value of x1, I got the value of x2, I got the value of x3. Now, how to apply this to calculate the reaction force? It is very simple. RB is equal to first load 100 multiplied by the corresponding ordinate is 0.2. So, RB that 100 multiplied by the corresponding ordinate 0.2. Okay, 50 multiplied by the corresponding ordinate 0.4. And then 200 multiplied by the corresponding ordinate 0.7. The summation of all these we are getting the value of RB. So, this is the way you can use the ILD to compute the reaction force. And quickly we can take one example problem because we have seen the how to calculate the reaction force for the concentrated load, and also we will see how to calculate the reaction load for the UDL. So you see here the simply supported beam is there, on the top of that 60 kilonewton per meter is acting. The length of the UDL is 4 meters and the length of the girder or the simply supported beam is 9 meters. What is asked to calculate is RB. We are going to calculate the value of RB. So, you know, for RB, I need to draw the RB diagram here. So, this is the ILD for RB. I'll write here, this is ILD diagram for RB. Now, what is the next step? I am going to project the loading, but that is the point load. Each and every point load I have drawn the ordinate. Here I need to draw the starting point and then ending point of the UDL. I am going to drop the ordinate. Okay, this is the starting point of the UDL and this is the ending point of the UDL. I have drawn the ordinate. Okay, so inside portion is shaded. The similar way I am going to calculate the ordinates. Okay. So, what is the major triangle? Major triangle is 1 divided by the total length of the span is 9. So, this is 1 by 9 equal to x1 divided by 1 plus 4, 5 meters. So, this triangle I am considering. Larger triangle, this 1 by 9. Smaller triangle is x1 by 5. And then same, this is 1 by 9 is a larger triangle, x2 by 1. Okay. I'll mark it in the smaller triangle. So, this is the smaller triangle, green color. So, we got the value of x1, x2. But if you see the point load, I'll go back here. Point load means that load multiplied by the ordinate. That's it. The summation of load, for example, 100 kilonewton multiplied by the corresponding ordinate plus the next load multiplied by the corresponding ordinate. But in this case, we need to calculate load multiply the area of the shaded portion here, where exactly the UDL is acting. So, you see RB is nothing but the intensity of the UDL multiplied by the area of the ILD under UDL. So, this is the shaded portion is the area of the ILD under UDL. So, 60 is the load multiplied by area. You see this shaded portion is nothing but the trapezoidal. So, trapezoidal formula you know, this is A plus B, that is x1 by x2 by 2 multiplied by h. H is nothing but the length in our case. So, length is we know 4 meters, A is we know it is 1 by 9, B is 5 by 9. Okay, A is equal to 1 by 9, B is equal to 5 by 9. We substituted that value. So, A is 1 by 9, B is 5 by 9 and this is the h value. We have substituted everything here, h is 4 meters, this is A plus B by 2, okay. In trapezoidal formula we substituted, we got the value of RB, okay. Similarly, we can able to, for a maximum reaction force, what we will do? If you want RA value maximum, we need to keep this moving load at the starting point, head of this load at the RA. If you want to maximum RB, we need to keep the tail of the load at the RB. So, what I have done? I have kept this moving load of 80 kilonewton per meter. The tail of the load I kept at B and then I am going to calculate the RB. So, this is the diagram for RB and then I have shaded the portion where the UDL is acting. Then I have computed the x1 ordinate by using the similar triangle principle. Now, the UDL multiplied by the shaded portion which is trapezoidal area. So, this is A. This is B by A plus B by 2 and then this is H. H is nothing but the 4 meters. Okay. So, H is equal to 4 meters. We substituted and we got the value of RB. For maximum RA, what I will do? I am going to keep the head of the load at the RA and then the diagram for the ILD for RA and then shaded portion. Using a similar triangle, I calculated the x1 value. And then the load multiplied by A plus B by 2 into H. What is A? A is equal to 1, B is equal to 3 by 4 by 2 and H is equal to 4 meters. Got it? So, I got the maximum RA value is 280 and then maximum RB value is 280. But you see, if the load is somewhere in between, I am getting the reaction force RB is less. So, this is the importance of the ILD diagram. Same load only based on the location, the intensity will vary. Okay. So you see, when you keep the head of the load at RA, we got the maximum RA value, and when we keep the tail of the load at the RB, we got the maximum value of RB. So I hope now you understood how to calculate the reaction forces for both the UDL and then point load. So at the summary in the lecture, end of the lecture, what we learned how to calculate the reaction force of a beam by using the ILD concept. So thank you for watching this lecture. Thank you.